Have you ever watched a robot arm move with perfect precision or a character in a video game jump and run so realistically and wondered, how do they do that? Well, it all boils down to one single fundamental idea. Today, we're cracking open the textbook Applied Dynamics to really get a handle on the secret language of motion, what we call degrees of freedom.
So here's how we're going to tackle this. First, we'll cover the absolute basics of describing motion. Then we'll get to the main event, what a degree of freedom actually is. After that, we'll look at some really clear examples, talk about the rules that limit movement in the real world, and finally, we'll put it all together and analyze the system step by step.
All right, first things first. Before we can figure out how something is going to move, we need to agree on how we even talk about motion in the first place.
Which brings us to the biggest question in all of dynamics, really. How on earth do we predict movement? I mean, where do you even start?
Well, the very first thing you do is decide what you're looking at. In dynamics, we call this the system. It could be something simple, like a baseball, or it could be a whole collection of parts, like a car engine. And the whole game is to figure out what inputs, like forces, are acting on that system to predict its output, which is, you guessed it, it's motion.
Okay, so we've got our system. Now we can get to the really cool part, the absolute heart of what we're talking about today. And that is, of course, degrees of freedom. Now, the textbook Applied Dynamics gives us this very official-sounding definition. A degree of freedom is the minimum number of independent coordinates required to describe the motion of a system completely.
Okay, I know, that sounds a little academic, right? So let's just throw that out for a second and simplify it. All you really need to ask is this: how many independent ways can this thing move? That's it. That's a degree of freedom. It's that simple.
You know, the best way to really wrap your head around this is to see it in action. So let's get our hands dirty and actually count the degrees of freedom for a few different things.
Let's start with this classic example, a simple bead on a hoop. Now think about it. The bead can't fly off, it can't move left or right on its own. It's stuck on that wire. It can literally only do one thing: slide along the path of the hoop. That's one independent motion. So it has exactly 1 degree of freedom. See? Easy.
Okay, time to level up just a little bit. On the left, you've got a tiny particle, just a dot, on a flat surface. And on the right, you've got a solid, rigid block on that same surface. They look pretty similar, but trust me, their freedom to move is not the same.
So let's break down that difference. The little particle can only slide. It can go left and right, and it can go up and down. That's 2 separate ways it can move, so it has 2 degrees of freedom. Now, the rigid body, it can also slide left and right and up and down, but, and this is the key, it can also spin in place. It can rotate. That rotation is a 3rd independent motion, so the rigid body has 3 degrees of freedom.
So if a block on a table has 3 degrees of freedom and an object floating in space has 6, you might be wondering, why isn't everything just flying and spinning around all over the place? Well, the answer is because of things that get in the way. We call them constraints.
A constraint is really just a rule. It's a restriction that limits how something can move. You can think of them as the laws of physics for that specific system. The floor is a constraint, a chain is a constraint, and as we'll see, a hinge is a really good constraint. They all take away freedom.
Oh yeah, a door hinge is the perfect example. Think about it. A door, if it were just floating in space, could move in 6 different ways. But that hinge, it physically stops the door from moving up or down, forward or back, and from tilting side to side or front to back. That's 5 restrictions, 5 constraints. So what's left? Only 1 possible motion, swinging open and closed, which means the door has just 1 degree of freedom.
And all of this leads to a super simple but incredibly powerful formula. The degrees of freedom, your DOF, is just the total number of ways something could move minus the number of constraints that are holding it back. It's that simple, potential motion minus restrictions.
Okay, so we've got the main idea, and we have the formula. I think it's time we put this all into practice. Let's use what we've learned and analyze something a little more complex.
Let's go ahead and tackle a problem straight out of the book. You've got all the tools you need now. You ready to give it a shot with me? Okay, here it is. We've got a tractor pulling a trailer, and they're both on a flat surface. The question is, how many degrees of freedom does this whole thing have? Now, there's one really important rule here. The wheels can roll, but they can't slip sideways. Keep that in mind.
All right, let's walk through this together. Step 1. What's the total possible motion? Well, just for a second, imagine they're not connected. The tractor is a rigid body, so it has 3 possible motions. The trailer is also a rigid body, so it also has 3. 3 plus 3 gives us a total of 6 potential motions. Easy.
Step 2. Now let's find the constraints. First, that pin joint connecting them. It stops the trailer from moving away from the tractor, both sideways and forwards. So that one joint is actually 2 constraints. Then we have the wheels. The rule is they don't slide sideways. That takes away 1 motion for the tractor and 1 for the trailer. So that's 2 more constraints. In total, we have 4 constraints. Step 3. Time to calculate. We start with our 6 potential motions. We subtract our 4 constraints.
And that leaves us with our final answer. The entire tractor-trailer system has just 2 degrees of freedom.
But what does the number 2 actually mean for the driver? It's actually incredibly useful. It means you only need 2 independent commands to control that entire complicated system. And for a truck, what are those 2 things? Steering and hitting the gas. That's it. With just those 2 inputs, you control the whole shebang.
And this right here is why this whole concept is so important. Figuring out the degrees of freedom isn't just some boring homework problem. It is the absolute first step for almost any dynamics analysis. If you're an engineer designing a robot, it tells you how many motors you need. If you're a game developer, it defines how your characters can move. Heck, it's even used to predict the orbits of satellites and spacecraft. It's everywhere.
So now you've got the basics down. You know how to think like a dynamics engineer. So I'll leave you with a little puzzle to think about. A regular bicycle moving on a flat plane, and its wheels don't slip. How many degrees of freedom do you think it has? It's a fun one to chew on.
That's all we've got time for in this explainer. Thanks for joining me, and as always, keep asking questions.